Well, welcome back to the flipped classroom here. Hopefully you're ready for our first fundamental theorem of calculus review, and we're going to add on to that some initial value problems. So let's go ahead and revisit that first fundamental theorem. If you recall, it said the integral from a to b of f prime of x is equal to, so remember we're going to integrate f prime, and who do I take the derivative of to get f prime? Well, that's f, and it's always upper minus lower, so f of b minus f of a. Now our goal is to look at this fundamental theorem in a different light today, so I'm going to go do something a little different. I'm going to go ahead and add f of a to both sides to balance it out, and bring it over here. And then I'm just going to reverse my equation. So on this side I'm left with just f of b, and I'm going to write that first, is equal to f of a plus the integral from a to b of f prime of x dx. So hopefully I didn't do anything too mind-blowing. Basically, I wrote out my first fundamental theorem, and I'm adding this term to the other side. And then I just kind of reverse the order how I've written it. So again, this is just our first fundamental theorem written in a different way. So I'm going to keep breaking it down here. Let's kind of go ahead and sketch this off to the side. So what we're saying is that this function, we're going to start it at a with this lower bound of a. So this is where I'm starting. This is like my initial value. And let's just go ahead and label this as initial. And b is where I'm ending. So this f of b is going to represent my end. So now we can say that this integral from a to b of f prime of x, you'll notice here, not only represents the area under the curve, it's representing the change in f of x, the difference in that upper minus lower. So, let's go ahead and jot down, this is representing the change in f of x. Now graphically, what does that look like? Well, let's go ahead and label this as our f prime of x. So we did say it's representing this area from a to b under the curve, but another way to think of it is the change in f of x. All right, let's go ahead and solve one graphically now with an initial value problem. And these are going to happen pretty frequently in our exam, and we just have to be really aware of them. So you'll notice it says the graph of f prime. So again, I think you're crazy if you're not writing f prime next to your graph. The derivative of f is shown in the figure above. If f of 1 equals 5, okay, so they're giving us an initial condition, things we need to be aware of. Then find the following. So I want you to pause me, take a few minutes, get this sketched out perfectly in your notebook so you have something to refer to. Now we've said before, you're kind of crazy if you don't sit here and put all your areas in. So I'm real quickly going to get my areas. So this is 4 by 2 divided by 2. So hopefully you're thinking that's an area of -4. And again, I would put it right in there to help yourself. I'm going to go get this side, 3 by 2, half of that. I'm going to say -3. Remember, if it's under the x-axis, we should be throwing a negative in front there. I'm going to draw that rectangle in there and say that's a -2 area. I'm also going to split these into triangles here, to get their areas. I'm going to say this is a 3/2. 3. And then of course, to get this goofy shape, remember we did one similar a couple days ago, you want to kind of build a rectangle around it. If you can picture a rectangle here, okay, so that looks like it has a base of 4 and a height of 3, so I would say the rectangle itself has an area of 12, but I need to kind of subtract out this circle piece, so I'm going to be left with this goofy shape. And our circle formula is pi r squared. I see half, so that's half pi r squared. Looks like a radius of 2. So I'm going to say this is 12 minus 2 pi. All right, I know that's a little sloppy in there, but you've done your own work, and we're going to easily compare. So our first question question A here is we want to evaluate f of 5. So remember, according to our first fundamental theorem, to get what we want to find, we simply have to set that equal to the initial condition, and if we look, that's our f of 1, plus the integral from what we want to find. Our start, remember, our initial means where you're going to start, that's always your lower bound, and we want to find our end value is our upper bound, we want to find 5, and we are integrating f prime of x dx. So I'm just going to scroll up a little here. F of 1, that initial value is 5, plus the integral from 1 to 5. We'll just kind of calculate your work there from 1 to 5. I would say that's 12 minus 2 pi. So hopefully we've got a total of 17 minus 2 pi. All right, so moving on, question B. Let's say we want to find f of 0. Okay, so what you're finding is going to come first. F of 0 equals that initial condition where you're starting, plus, remember that initial condition, your starting point is your lower bound, to what you're finding is the upper bound. Okay, what you're finding is always the upper bound, even if they're in the wrong order. Let's make a note in your book there. What you're finding better be the upper bound. Your initial condition is the lower bound. So in this case, you'll notice we are definitely in the wrong order. So f of 0 is now going to be equal to f of 1 minus the integral from 0 to 1 of f prime of x. So I can say that value f of 1 was 5 minus whatever this area happens to be. So we're going to go back and we're going to look from 0 to 1. I'll have to scroll back up here. 0 to 1, it looked like I had an area of 3/2. So I'm going to say 5 minus 3/2. So I've got 10/2 minus 3/2 for a total of 7/2. All right, we're going to keep chugging there. Remember, what you're finding comes first, and that's your upper bound. So letter C. Let's say we want f of 11. All right, go ahead, set up your integral. Pause me and see if we get the same thing. So hopefully our integral looks the same. So f of 11 is equal to that initial value of 5 plus, go ahead, pull up your area, see what you get there. So feel free to check my work here. I'm going to take the 12 minus 2 pi plus 3 minus 3, of course those cancel, minus 2, add that to my 5, I've got a 15 minus 2 pi. All right, last one of this group. Again, try it on your own and then see if we've got the same answer. Let's say for D, we want to find f of negative 4. So set up that integral and then compare answers with me in a moment. And hopefully you follow my work okay. I've got my negative 4 equals, I want to stress this is the initial value, plus the initial value goes on the bottom to 5 of f prime of x. So you'll notice that my bounds were backwards, so I switched and pulled out a negative. So I've got negative 4 minus 3/2. I distributed that negative through, and I got a total of 15/2. All right, question 3. The velocity is equal to 3t squared plus 8t for any time greater than 0. If the position of the particle at t equals 2 is 5, what is the position of the particle at t equals 4? Well, hopefully you've caught on by now, and we're thinking we have velocity, and the question is about position. So I'm going backwards. In order to get from velocity to position, we have to integrate. In integration, we should be thinking first fundamental theorem of calculus. And hopefully you've picked out that we have an initial condition. All right, so let's just identify that initial condition. When the time is 2, the position is 5. So I'm going to say x of 2 is 5. So when the time is 2, the position is 5. And the question is asking, what is the position when the time is 4? All right, so this is just setting you up perfectly for first fundamental theorem of calculus. Remember, the one thing we want to get down today is that end value that you want is equal to the initial plus the integral of the change. Okay, the n value is equal to the initial condition plus the integral of the change. So I'm just going to scroll down here. The n value that I'm looking for is the position at 4. The initial value given is the position at 2, plus the integral. My bounds are clear. If I'm using 4 and 2 here, those are my bounds. From 2 to 4. Okay, remember that initial bound goes on the bottom. And, well, what am I integrating? That function was 3t squared plus 8t dt. And once you've set that up, the rest should be pretty straightforward. The rest is just simple calculus. We just have to get this formula down in our heads today. The n value is the initial plus the integral and the change. And remember, this initial value should match with this lower bound. So go ahead, integrate this function on your own, plug in your bounds 2 and 4, and we'll see if we get the same thing. So pause me and try it on your own. Well, hopefully you follow my math here. I've got my n value, and my x of 2 is 5. I've got t cubed plus 4t squared when I integrated. Plugging those numbers in, I'm going to get an x of 4 is equal to 5 plus, this is 128 minus 24, so 5 plus 104. Hopefully gets us a final answer of 109. So the position at 4 is 109. All right, question 3 is a pretty common applied position velocity acceleration problem. So you'll notice they're telling us the velocity is 3t squared plus 8t for any time greater than 0. At t equals 2, the position is 5. What is the position at t equals 4? So very similar to what we did for our first example. We have this initial condition. I just want to stress the initial condition. When the time is 2, the position, so x of 2 is 4. Okay, so at time t, the position is 4. The question is, what is the position at 4? All right, so we've just identified our initial condition and what we're asked to find. And remember that initial condition is like the start, the find is what we're finding in the end. So we're just going to use that first fundamental theorem of calculus, kind of the rewritten version. Remember, it's that n value is equal to the initial plus the integral of the change in position. Okay, so that's exactly how I'm going to set it up. I'm looking to find, this is what I'm finding, my n value, the position at 4, so let's use x of 4, given I know the position at 2, plus, remember initial always goes on the bottom, what you're finding, the n value should be on top, and I'm clearly integrating velocity, which is 3t squared plus 8t. So to get this position function, I have to integrate velocity. Hopefully that's pretty obvious. Initial goes on the bottom, what you want to find goes on top. So now we'll just keep going with it. X of 4 then is equal to, we said we had an initial value of 5, plus, just go ahead and integrate here. I've got t cubed plus 4t squared from 2 to 4. Take your time with that definite integral, plugging those numbers in. And hopefully your work matches with mine. I've got 64 plus 64. Obviously you can keep reading for a final answer of 109. All right, let's try a similar problem. All right, number 4. Acceleration is sine of pi t over 4 for t is greater than 0. They give me the velocity, and they want to know a velocity at a specific time. So hopefully you're thinking by now, first fundamental theorem, in order to get from acceleration to velocity, hopefully that's clearly an integral, and remember again, it's that n value equals the initial plus the change in velocity. So I'm going to find, v of 3, I want the velocity at 3, when I know the velocity at 0, plus the initial goes on the bottom, which you want to find on top, and I'm integrating a of t dt. So pause me there, go for it on your own, see what you get when you integrate, and we'll see if we get the same thing. Hopefully you're seeing u sub there. Pi over 4t du is equal to pi over 4 dt. When I solve, I'm basically going to multiply by the reciprocal, so I get 4 over pi du equals dt. So I've got v of 3 is equal to 6 plus 4 over pi, the integral of the sine of u du. Okay, I substituted this into my dt. Maybe you can do that in your head by now. Who do you take the derivative of to get sine? Hopefully you're thinking negative cosine of u. And I'm going to worry about my bounds. Remember, if I leave it in terms of u, I've got to use u bounds. So I did have a 0 and a 3. When I plug 3 in, I'm going to get 3 pi over 4. And when I plug 0 in, I'm going to get just 0. So as I carefully go, I'm going to get 6. I'm going to pull out that negative so it doesn't interfere. And that's the cosine of 3 pi over 4 minus the cosine of 0. And hopefully we're just cleaning up still. You know, it's totally personal preference here. I'm going to get a common denominator inside and say that's negative radical 2 minus 2 all over 2. And then I'm going to multiply these two terms together. So I'm going to say that's 6. I'm going to distribute my negative as well. So I'm going to get plus 4 radical 2 plus 8 all over 2 pi. And really the only thing I can do is divide those terms by 2. So I'm going to say 6 plus 2 radical 2 plus 4 over pi. And not pretty, but we've definitely got a final answer there. Well, folks, we've made it to the last problem of the night here. So we've got a pizza, and I'm sure you can all picture this, is heated to a temperature of 400 degrees Fahrenheit. It's taken out of the oven and placed in a 75-degree room at time t equals 0. The temperature of the pizza is changing at a rate of negative 3 radical t degrees Fahrenheit per minute. To the nearest degree, what is the temperature of the pizza at t equals 4? So lots of things to consider here. First of all, they tell me this is degrees Fahrenheit per minute, and they want my answer to be about degrees. So when I integrate, I'm going to lose the per minute. When I take a derivative, I'm going to add on the per minute. Since I want to lose the per minute, I know I'm integrating this function. And they've also given me an initial condition. All right, so we have to use our first fundamental theorem. The initial value says at t equals 0. Now be careful, they gave you two pieces of information. They gave you a pizza heated to a temperature of 400, and then they told you about the room. And one of them we don't need to deal with at all. Since the whole question is about temperature of the pizza, they're really just throwing that 75 in there, to kind of mess with you a little bit. You don't actually need that value. That has nothing to do with the temperature of the pizza. So at t equals 0, the pizza has a temperature, I'm going to use capital T for temperature, of 400 degrees Fahrenheit. All right, so that is my initial condition. Well, what do they want you to find? They want you to find at t equals 4, what is that temperature of the pizza? So hopefully you're running through that first fundamental theorem in your head, saying that n value that you want is equal to the initial value plus the change. All right, so I want to find, I'm going to use capital T for temperature, the temperature of the pizza when my time is 4, and my initial temperature, so t of 0, plus the integral, remember what you know goes on the bottom, what you want to find goes on top, from negative 3 radical t dt. So again, take your time, integrate. It's not a crazy u sub, just a nice easy integral, and compare your final answer with me in the end. So hopefully we ended up having the same work here. So I've got my T of 4 equals T of 0. I integrate there, so my T of 0, my initial temperature of the pizza, remember nobody cares about the room, the pizza temperature was 400. This was T to the 1/2, so I got T to the 3/2 times 2/3. My 3's are going to cancel, so I have my -2. Carefully plug in the upper bound minus the lower bound. So I've got -16 minus 0 for a total of 384 degrees after 4 minutes. Well, hopefully this section of the first fundamental with initial condition wasn't too hard for you, and we look forward to seeing you in class tomorrow.